Have you ever held an apple in your hand, felt its smooth skin, smelled its sweet aroma? It's a simple, familiar object. But hidden within this everyday fruit is a profound truth about our universe. Everything, from the apple itself to the hand that holds it, is made of atoms. Atoms are the fundamental building blocks of matter. They are incredibly small, far too tiny to be seen with the naked eye. Imagine cutting that apple into smaller and smaller pieces. Eventually, you would reach a point where you could cut no more. You would have reached the realm of atoms, but what exactly is an atom, and just how small is this fundamental unit of existence? To grasp the true scale of an atom, we need to embark on a journey into the unimaginably small. Picture a single drop of water. It seems like a tiny thing, yet within that single drop, there are trillions upon trillions of atoms. That's more atoms than there are stars in the observable universe. The size of an atom is so incomprehensibly small that it's impossible to see directly, even with the most powerful microscopes. We can only infer their existence and properties through indirect observations and experiments. Let's try a thought experiment to visualize the atom's size. Imagine inflating an atom to the size of a grapefruit. On this scale, the grapefruit would be so large that it could encompass the entire Earth. And within that grapefruit, the original atom would be about the size of a period at the end of this sentence. This incredible disparity in scale highlights just how small atoms truly are. They exist in a realm far beyond our everyday perception, a realm we can only begin to comprehend through the power of scientific inquiry. Section 5. The heart of the atom. Despite their infinitesimal size, atoms are complex structures with their own internal components. At the heart of every atom lies the nucleus, a dense central region that contains two types of particles, protons and neutrons. Protons carry a positive electrical charge, while neutrons have no charge, making them electrically neutral. Together, protons and neutrons account for almost all of an atom's mass. Section 6. Electrons in orbit. Orbiting the nucleus is a cloud of even tinier particles called electrons. Electrons carry a negative electrical charge and they are constantly in motion, whizzing around the nucleus at incredible speeds. The number of electrons in an atom is equal to the number of protons, ensuring that the atom as a whole is electrically neutral. The interactions between these charged particles, the attraction between the positively charged protons and the negatively charged electrons, are what hold the atom together. Section 7. The elements of existence. The number of protons in an atom's nucleus determines what element it is. For example, all hydrogen atoms have 1 proton, all carbon atoms have 6 protons, and all oxygen atoms have 8 protons. This number is known as the atomic number, and it's a fundamental property of each element. In addition to protons, atoms of the same element can have different numbers of neutrons. These variations are called isotopes, and while they don't affect the atom's chemical properties, they can influence its stability and radioactivity. Section 8. Atoms united. Atoms are not solitary entities. They are constantly interacting with one another, forming bonds and creating the molecules that make up our world. These interactions are fundamental to the existence of matter as we know it. Without these bonds, the universe would be a vastly different place, devoid of the complex structures that we see around us. These bonds arise from the interactions between the electrons in the outermost shells of atoms. Electrons play a crucial role in determining how atoms bond and interact with each other. The behavior of these electrons is governed by the principles of quantum mechanics, which dictate the probabilities of where electrons can be found around the nucleus. There are several types of chemical bonds, each with its unique characteristics. The nature of these bonds determines the properties of the resulting molecules and materials. Understanding these bonds is essential for fields ranging from chemistry and physics to materials science and biology. Covalent bonds involve the sharing of electrons between atoms, creating a strong bond that holds the atoms together. This type of bond is common in organic molecules, which form the basis of life. For example, the DNA in our cells is held together by covalent bonds. Ionic bonds, on the other hand, involve the transfer of electrons from one atom to another, resulting in the formation of positively and negatively charged ions. These ions are then attracted to each other, creating a bond. Ionic bonds are typically found in salts, such as sodium chloride, which is common table salt. Metallic bonds found in metals involve a sea of electrons shared among a lattice of positively charged metal ions. This unique bonding gives metals their characteristic properties such as electrical conductivity, malleability, and ductility. The free movement of electrons within the metal lattice allows metals to conduct electricity efficiently. In summary, the interactions between atoms and the bonds they form are the foundation of the material world. By understanding these bonds, we can manipulate and create new materials with desired properties, leading to advancements in technology, medicine, and countless other fields. Section 9. Water and salt. Examples of atomic bonding. In this section, we will explore the fascinating world of atomic bonding by examining two common substances that we encounter in our daily lives: water and salt. These substances provide clear examples of how atoms come together to form molecules and compounds through different types of bonding. Let's take a closer look at these two familiar substances, water and salt, to see how atomic bonding works in action. Understanding the bonding in these substances will give us insight into the fundamental principles that govern the behavior of atoms and molecules. A water molecule, H2O, consists of two hydrogen atoms covalently bonded to one oxygen atom. This type of bonding is known as covalent bonding, where atoms share electrons to achieve stability. The sharing of electrons allows each hydrogen atom to have a full outer shell, while the oxygen atom also achieves a stable electron configuration. The oxygen atom shares its electrons with the hydrogen atoms, creating a stable molecule with a bent shape. This bent shape is due to the repulsion between the lone pairs of electrons on the oxygen atom, which pushes the hydrogen atoms closer together. The result is a molecule with a unique structure that gives water its special properties, such as its high boiling point and ability to dissolve many substances. Table salt, on the other hand, is made up of sodium chloride, nasal. Unlike water, the bonding in sodium chloride is ionic, not covalent. In ionic bonding, atoms transfer electrons to achieve stability, resulting in the formation of ions. In this case, an electron is transferred from a sodium atom to a chlorine atom, creating ions, atoms with a net electrical charge. The sodium atom loses an electron to become a positively charged sodium ion, Na+, while the chlorine atom gains an electron to become a negatively charged chloride ion, Cl. The positively charged sodium ion and the negatively charged chlorine ion are then attracted to each other, forming an ionic bond. This electrostatic attraction between oppositely charged ions results in the formation of a crystal lattice structure, which gives table salt its characteristic shape and properties. The strong ionic bonds in sodium chloride make it a stable compound with a high melting point and the ability to conduct electricity when dissolved in water. By examining these examples of atomic bonding in water and salt, we can see how different types of bonds, covalent and ionic, play a crucial role in determining the properties and behavior of substances. Understanding these fundamental concepts helps us appreciate the complexity and beauty of the molecular world around us. Section 10. Atoms, the foundation of reality. From the smallest speck of dust to the largest star in the cosmos, everything we see and touch is made up of atoms. These atoms are incredibly small, so tiny that millions of them could fit on the head of a pin. Yet, despite their minuscule size, they hold the secrets to the vastness of the universe. These tiny particles are the fundamental building blocks of the universe, the Lego bricks of reality. Just as Lego bricks can be assembled into complex structures, atoms combine in countless ways to form everything we know. From the air we breathe to the water we drink, from the food we eat to the stars we gaze at, atoms are the essential components. They are the source of all matter, energy, and complexity that we observe in the world around us. Atoms interact with each other through forces that govern their behavior, leading to the formation of molecules and compounds. These interactions are the foundation of chemistry and physics, the sciences that explain how our world works. Understanding atoms is not just about unraveling the secrets of the microscopic world, it's about delving into the very essence of what makes up everything. Scientists use advanced tools and techniques to study atoms, revealing their structure and behavior. This knowledge has led to groundbreaking discoveries and innovations, from the development of new materials to the creation of powerful technologies. It's about understanding the very fabric of our existence. Atoms are not just particles. They are the threads that weave the tapestry of reality. By studying them, we gain insights into the fundamental principles that govern the universe. This understanding helps us appreciate the complexity and beauty of the world we live in. It allows us to answer fundamental questions about the nature of matter, the origin of the universe, and the processes that govern the world around us. How did the universe begin? What are the forces that hold it together? How do atoms come together to form the diverse array of substances we encounter every day? These are the questions that drive scientific inquiry and fuel our curiosity. As we continue to explore the atomic world, we unlock new possibilities and expand our understanding of the universe. The study of atoms is a journey of discovery, one that takes us from the smallest particles to the grandest cosmic structures. It is a testament to human ingenuity and our relentless pursuit of knowledge. In essence, atoms are the foundation of reality. They are the building blocks that construct everything we see, touch, and experience. By studying them, we not only uncover the mysteries of the universe, but also gain a deeper appreciation for the intricate and interconnected nature of all things. The journey into the world of atoms is a journey into the heart of existence itself. Section 11. Unlocking the atom, unlocking the future. The discovery of the atom and its subatomic particles has revolutionized our understanding of the universe and has led to countless technological advancements. From nuclear energy to modern electronics, our ability to manipulate and control atoms has transformed our world in profound ways. As we delve deeper into the mysteries of the atom, who knows what incredible discoveries await us? Perhaps one day, we will unlock the full potential of these tiny particles, leading to new technologies and innovations that will shape the future of humanity.